So today I will be talking about curve counting in enumerative geometry. So let me first introduce the subject enumerative geometry, and then I will be talking about curve counting in two different setups. So let me start with the following picture. So let's say we are in CP2, which is complex two-dimensional manifold. And so suppose I have a point here, let's say P. Then if we want to draw lines, then we can certainly draw infinitely many of them, right? Now, if we choose another point, let's say Q, which is distinct from P to Q, then we have only one unique line, right? So this enumerative geometry deals with such kind of questions. So more importantly, so we are basically focused on enumerating various kinds of geometric objects satisfying certain type of constraints. So what are my geometric objects? So those geometric objects are various kinds of curves, or maybe those are hypersurfaces. Even modern techniques are counting sieves also. And then we have to impose the certain kind of constraint to get some finite answer. So for example, in this picture, so what is the slogan? So slogan is that we are starting with a compact complex manifold, and we are introducing certain condition onto it, so that these conditions reduces the dimension of this manifold one by one generically, and then at the end we are getting a zero-dimensional compact manifold, which is nothing but a bunch of points, and we are counting those points, right? So in this case, this is one. So usually these problems are very easy to state, but finding solutions are very clumsy as well as needs various techniques from various subjects. So one of the simplest kind of question is, we can ask that how many degree D curves are there in CP2? So by P2 I mean CP2, passing through this many number of points in general position. So by general position I mean almost all the points. So for example, if D equal to 1, then we will be requiring 2 points, which is the picture. So let's understand the case for D equal to 3. So that might give you some intuition. So we are actually want to understand cubics inside CP2. So what are the cubics? So these are vanishing set of degree 3 polynomials, homogeneous polynomials, right? So if you want to specify a cubic inside CP2, you only need to identify those 10 coefficients AI, right? And all of them are not zero. So essentially, this tuple AI will give you one cubic in the plane. So if you want to parameterize all the cubics in CP2, you only need to do the tuple A1 till A10 modulo C star X. So that's basically P9. So what I'm saying, a generic cubic inside CP2 will correspond to a point inside CP9. So if we ask the innovative question, so basically what we are, so we are in the first stage. So we are basically parameterizing our object in a nice compact manifold, that is CP9. Now the next step is we will introduce certain conditions so that we can reduce the dimension one by one generically. So this passing through point is basically, so if you choose some point, then passing through point is nothing but a hyperplane, right? And passing through the 9 points will give you, so if you can do it in linear algebra, so this is giving you 9 equations in 10 variables, and you can see that this has one-dimensional solution. But this is not always true. So this is true provided your conditions are generic, which is basically they are intersecting transversely. And if you want a projective solution, this is just 1 point, right? So now in modern theory, we can rephrase this as follows. So we have parameterized our space to be CP9. So that's basically space of all cubics. And we are saying that this cubic passing through 1 point is a hyperplane. So passing through 9 point is basically h to the 9. So we are basically computing the intersection product of h to the 9 against the fundamental class of P9, right? So that's basically 1. So these are all very nice. So once we count all the smooth things, so let's introduce the singularity. So by this picture A1, I'm basically saying this is local picture of this node. So this local equation would be, so if you take analytic coordinate xy, then this local equation would be x square plus y square. Similarly, cusp would be x square, y square plus x cube, and so on. So this middle picture is basically the cusp. The third picture is the tag node, and so on. So what I'm talking about is the AK singularity. So there are other kinds of singularity, but I'm skipping those for now. So now you can rephrase your question in terms of this singularity. So you can say that, so earlier my question was, I'm counting plane cubics through 9 points, right? Now I drop 1 point and then say this plane cubics pass through 8 points. And one more, now I have one more freedom. So that one more freedom I am fulfilling with the node. So yeah, so let me, I will ask you to believe me that this imposing a node is basically saying a one coordination one condition. So then second question I can ask that, can you count cubics with 2 nodes, right? Passing through 7 generic points. And so we can also ask that how many degree D curves are there through delta D minus K points with AK singularity. So there is a red because this is very difficult and only one conjectural solution is there, but that's not explicit. So let me introduce a breakthrough in this kind of question. So this is, so the question 1. So question 1 actually solved around 1880. So 1846, but after that there were no development. And then in around 1995, Caporoso Harris found the solution for this. So this A1 till, so delta many things. So these are actually delta many nodes. So you want to count all the degree D curves with delta many nodes. So this Caporoso Harris, they have explicitly computed that, and their method actually computes. So for example, if you want to count degree D curves with 10 nodes, so their method reduces it to computation of, let's say, 9 nodes and tangencies. And finally, if you get on reducing, then it's basically a point, I mean, counting tangencies. So nodal question get converted into tangencies, which are often easier. So in this context, so yeah, so let me mention what is the main difficulty in this kind of questions. So for example, if you want to count curves with 2 nodes, so these black dots are, sorry, the red dots are the nodes. If you want to count curves with 2 nodes, in that family, you will always get this bad locus. So this is basically the tag node. So then you have to know the computation of this chap. So there are 2 levels of difficulty. One is that when you are considering delta many nodes, you have to know that what other bad things it degenerate. So once you identify that, you have to also compute its contribution to that calculation. So they have systematically done that. So that is why these problems are very difficult to explore. So in this setting, we have studied this. So let me explain the picture. So you have a divisor in CP2, and I am looking at degree D curves where I have delta 1 many nodes. So this A1 meaning nodes, A2 meaning cusp. So we have delta 2 many cusp, and then so on, delta K many AK singularity. So if you impose all of those singularities, and then one more extra thing is that this resultant curve is actually tangent to that divisor. So if you want to compute this kind of system, then so this is actually an enumerative question. So we have.
You have 5 minutes left.
Yeah. So we have systematically solved this. So for example, degree 4 thing. So degree 4 curve with A3 singularity and tangency to first order is 368. Similarly, so we considered any degenerate singularity and any order of tangencies tk1 till tkn. So this is a joint work with Ritik Mukherjee. So let me mention another setup. So yeah, so let me right. So here there are many rooms, but at least these pictures will convince you that you have to look for the exotic things. That is the purpose of these pictures. Okay, so let me move on to the another setup. So that in that setup, we are actually dealing with so in earlier setup, our parameter space on which we are parameterizing our degree D curves are the projective space, but of large dimension. But in this setting, we are considering modular space M bar 0 and P2D. So this is known as Kontsevich modular space of stable maps. So these are actually parameterizing this data. So C is the genus 0 curve, which is basically, I mean, if you take smooth things, then it is topologically S2. And then N marking X1 through Xn, and then the map C to P2. So this is the degree D map, which you can say push forward of the class is D. And there is a technical condition, which is basically stability. So if you parameterize all of this, so you will get this modular space. So for now, I only ask to believe me that this is a nice space, a compact space where we can do intersection theory. And this dimension is also computed. So this dimension is 3D minus 1 plus n. N is the number of marking. Then you can define Gromov-Witten invariant, small nd, as follows. So you have a evaluation maps for each of the markings. So then you take the point class inside P2 and you pull back them and take the cup product and you integrate against the modular space. Of course, this integration makes sense only if the total codimension is same as the dimension. Otherwise, it's formally 0. So then the question is, can you count these NDs, right? And this is kind of a great breakthrough in our subject, which is due to Kontsevich and Menin, and independently Ruan and Pian. So they have found this beautiful recursive formula, which is, I mean, which is in a sense beautiful in the sense that you don't need any other a priori assumption. You only need to know what is N1, and then any ND can be recursively computed. And N1 is just simply this picture. So this is extremely beautiful. So you, following this phenomena, we have basically extended this result in what is called planar curves. So I'm not mentioning that, but yeah, so this techniques is extremely modern. Yeah, thank
you. Thank you very much. We have time for a couple of questions. Victor, Rajesh.
Yes.
Hello.
Right.
Yes. So this formula you just showed, the formula for just the previous slide.
Oh, so this Gromov-Witten invariant?
Yes.
This one? Yeah.
Do you know, I was wondering, is there a physical interpretation of this formula? In terms of maybe topological string theory or?
Yeah, so these are predictions from some from string theory, but I don't really know what are the elements. Yeah.
Thank you.
Yeah. Firstly, just to respond to Victor's question, yes, I think you can get these recursion relations. People have derived these recursion relations using physics reasoning, using topological string theory.
So for Calavier threefold, this is very relevant question because CDGP paper already predicted that, and mathematicians do verify this.
Yeah, but even for non-Calabi-House, for these like P2, you can still define a certain A model, sigma model, and I think even people like Itzikson and others, I think,
Right.
had reproduced also some of these things from physics reasoning. But I had a question, which is to try to connect to the first part of your talk about with these nodes.
Yes, yes. So let me
Generalization of this to the Kontsevich type calculations with nodes. Is there a
yes. So there is a indirect relation. So for example, let's look at d equal to 3. So I haven't written down the numbers. So for d equal to 3, this recursion will give you 12, right? And on this setup, yeah. So if you consider the question 1, so the answer for the question 1 is also 12. So this similarity. So let's say this is your number of qubits through A1 singularity. So this is 12. Similarly, small nd, which is 3, this is also 12. So why they are same? Because so any generic qubit is basically genus 1, and you impose one node, so that imposing one node actually kills off the genus. So finally you are getting genus 0 curve. So those numbers ought to be the same. But yeah, this phenomena will go on for higher genus, but you need to impose more singularities.
Okay, let's thank the speaker again. We'll move on to our next speaker.